Hello and welcome to EEE 41 Lecture 14, where we'll introduce the bipolar junction transistor, or the BJT. In this lecture, we'll discuss the structure and fundamentals of bipolar junction transistors and also its performance parameters. Our objectives for this lecture are the following: to draw the structure and identify the critical properties of a good BJT, review the charge transport in a biased PN junction, explain the charge transport in a forward active biased BJT, and lastly, compute the BJT performance in terms of carrier currents. Let's start with transistors. Transistors are electronic devices with at least 3 terminals that are used as a switch or as an amplifying element. Unlike in diodes, where the same pair of terminals act as both the control and controlled portions, in a transistor, the third terminal allows different terminals for the control input and the controlled output. The two most commonly used transistors today are the MOSFETs and the BJTs. MOSFET stands for metal oxide semiconductor field effect transistors, and as the field effect in the name suggests, this device works based on the concept of carrier drift. The term CMOS, however, refers to the technology of having complementary MOSFET types, the P MOSFET and the N MOSFET, in the same chip. CMOS technology has propelled the IC industry for the past 30 to 40 years and is the heart of most modern processors. MOSFETs has replaced BJTs in most IC products because of its higher density and lower power. High density means that more transistors and thus more functionality can be packed in the same chip area as compared to BJTs. MOSFETs also consume lower power because of the small current needed to maintain the on and off states of the MOSFET. CMOS operation also allows to have small currents when digital circuits are static or not switching. The second most common transistor is the BJT and is still preferred in some analog and digital circuits because of its speed and superior gain over the MOSFET. BJT, on the other hand, is based on diffusion. It offers faster speeds because of the smaller capacitances involved, but its higher power dissipation limits the amount of applications where BJTs are used. BJT dimensions are also harder to shrink and thus have lower density and would cost more in terms of the number of transistors per unit area of the chip. The bipolar junction transistor, or BJT, comes in two types, the PNP and the NPN, and as the name suggests, PNP is composed of two P-type regions with one N-type region in the middle, while NPN transistors are made of two N-type regions with a P-type region in the middle. BJT terminals are named as emitter, base, and collector. The same terminal names are used for both NPN and PNP. Shown here is the symbol for the PNP, where the arrow points into the device, and NPN, where the arrow points outward from the device. In the symbol, the terminal with the arrow is the emitter, the one at the middle is the base, and the other terminal is the collector. And given these terminal names, we can actually define voltages, for example, VEC, with the plus side at the emitter at the first letter, and the minus terminal at the collector or the second letter. So VCB should have the positive terminal at the C, negative terminal at the B. VEB would have a positive terminal at the E and negative terminal at the B. Alternatively, we can also define VCE, where the positive is at the collector and the negative is at the emitter, and so on and so forth. Now, given this definition of voltages, we can actually perform a KVL. So for example, going clockwise, we can write VEC plus VCB minus VEB to be equal to 0, meaning if we know VEC and VCB, then we can solve for VEB. Or more generally, if we know the voltage across any two pairs of terminals, then we can actually solve for the voltage across the third pair of terminals. In terms of current, we have emitter current IE, collector current IC, and base current IB. We'll use this notation for the direction, which is consistent with the one found in the book. However, this notation does not follow the standard IEEE convention, where positive current flows into the terminal, meaning under IEEE convention, IE, IB, and IC all both points towards the device regardless if it is NMOS or PMOS. Now, that convention can be most commonly found in simulators. However, in our discussion, again, we'll follow this notation right here. Now, the notation that will follow, the one used in the book, can be remembered easily using the help of the arrow shown. Now, the arrow in the emitter will be consistent with the direction of the emitter current for both PNP and NPN. So here the arrow is outwards, so IE is outwards. Now, the base current will then follow from the arrow. Here, the arrow is downwards, so IB must be downwards. The arrow is upwards, so IB is upwards. And the same is true for the collector. If we follow the direction of the arrow, then the collector must be rightwards in this direction. And in this symbol, the arrow is leftwards, and so IC must be leftwards. So for some practice, consider this symbol here. Now, since the arrow is outward of the device, then this must be an NPN transistor. The terminal with the arrow is the emitter. The one at the middle is the base, where the other terminal is the collector. In terms of currents, we can follow the direction of the arrow. So IE must be downwards. IB must be rightwards. And then lastly, IC must also be downwards. Now, if for the voltage we were able to perform KVL, then for the currents, we can actually perform KCL. So if we do KCL here, current going in is IE, and the two currents going out are both IB and IC. So we have IB plus IC, and therefore, if we know IB and IC, we can solve for IE. If we know IB and IE, we can solve for IC, and so on. Now, this equation is also applicable for NPN. If you perform KCL here, then this equation should still hold true. Now, let's discuss the charge transport in a BJT. But before starting with that, we'll review first what happens in a PN junction, specifically under reverse bias conditions. So when we reverse bias our PN junction, our ID is approximately IS in terms of magnitude. So here, ID is approximately negative IS, and it is actually fairly constant regardless of the voltage. And this actually tells us that somehow we can model this portion as a constant current source. Now, we'll translate later on how this constant current source behavior is achieved in a BJT. Now, this IS, the reverse saturation current, depends on the rate of minority carrier near the junction. Inspecting further, IS is proportional to this term right here, where if we have ND much greater than NA, so that will focus only on one side. Then we'll just remove the term where the ND is at the denominator and end up with this one. So in this example, we have the N side at the left and P side at the right side. And since ND is much greater than NA, then we have here that the minority carrier equilibrium concentration is lower at the N side because the doping concentration there is higher compared to the P side. Now, if we reverse bias the junction, then the applied voltage will tend to decrease the carrier concentration near the edge of the depletion region, and carriers will actually generate along the way until it reaches the thermal equilibrium condition far from the junction. Now, if we look or if we inspect this further, this Ni squared over Na term actually refers to this Pn naught, or the height of this line. Now, Ln refers to the minority carrier diffusion length, and if we say approximate Ln to be this portion here, then this tells us that the amount of current we'll get under reverse bias is approximately dictated by this area right here. So if we integrate that, then we'll get some amount of charge, and that amount of charge is actually being generated and is flowing through our device every tau seconds. Okay, so this area right here corresponds to some charge Q, which is generated every tau second. So we get the current. Now, in terms of EBD, we show here the EBD of a reverse biased PN junction, where we have here the N side and we have here the P side. Now, the only currents, the only carriers involved in this reverse current are the minority carriers crossing from this point to this point, and the holes from this point to this point. Now, because of the electric field here, this minority carrier hole are swept to the other side, and therefore there is very low electron concentration at this portion because they are being swept on the other side. On this portion, there is very low hole concentration because they are being swept on the other side. And to maintain this current, we are actually waiting for carriers to randomly get to this point before being swept to the other side. And what actually feeds that is because since these carriers are drifting to the other side, then there must be lower carrier concentration on these portions at the edge of the depletion region, and by random thermal motion, carriers will diffuse nearer or will have a net movement towards this portion where there is a smaller carrier concentration. And once they get into this to this point, then that's when they start drifting to the other side. Now, one notable behavior that we are observing is that even if we reverse bias this junction further, then we'll just get the same amount of current because the carriers that are being fed is not affected by this, is not mainly dictated by this electric field right here, but mostly because of the random movement that caused them to get here before they are being drifted to the other side. So we can actually increase the reverse current by increasing the rate of minority carrier generation. Again, note that there is small or less carrier concentration, minority carrier concentration at these portions near the depletion region edge. And if you remember, the more missing carriers there are, then the stronger the rate of generation is. However, when we reverse bias our PN junction, since we already have a very small amount of minority carriers at the depletion region, reverse biasing it further does not actually get this plot much lower, because this is approaching zero already, meaning as we reverse bias the device, this point actually remains mostly at the same place, and therefore we get the same rate of generation, and therefore we end up with approximately the same current. Now, to increase this reverse current, what we can do is to first we can apply light to excite carriers at the junction, and when the carriers are generated at the junction itself, then there would be more additional reverse current that will flow in our PN junction. And this technique is actually used in photodiodes to detect light. So meaning the stronger the light you have, then the more current you get. And what actually happens to the IV curve is you are actually getting more current for the same amount of bias that you apply, and therefore this technically shifts the IV curve of your device. And so with this behavior, the changing current based on light, photo detectors can detect light. Now, another option to increase the reverse current is to actually inject minority carriers into the neighborhood of the junction. So instead of relying only on the carriers that are generated at this portion, we actually inject new carriers, and when they get at this point, then they will just drift into the other side, and so we get more current. Now, this scenario here is what actually happens in our BJT. And since this one is a reverse bias, we can actually, or changing the voltage here does not actually change the current much. We can actually control the current by controlling the amount of injected carriers. And so this one actually allows us to operate the BJT, the output of the BJT, to act like a current source by controlling only the amount of carriers injected. Regardless of the voltage at this portion, we get the same amount of current. So here we'll discuss what we call the forward active operation of our BJT, specifically the PNP version. So this is just a qualitative discussion of what happens in a forward active bias PNP BJT. Now, to be in the forward active mode, the emitter base junction must be forward biased, whereas the collector base junction must be reverse biased. Now, these two voltages right here can be seen if we look at the junction as separate PN junctions. So for the emitter base junction of a PNP BJT, the diode will be oriented in this manner. So the P side is the anode, the N side is the cathode, and to forward bias this, we need to apply a positive voltage to this diode. So the P side is the emitter, and so this E right here refers to the P side, and this B right here refers to the n side, and therefore we simply get that some VPN is greater than 0 for it to be forward biased. For the collector base junction, we need to reverse bias it, so we apply a negative voltage to the junction, with the collector side considered as the P side and the base side considered as the N side. So this will be the case, or the voltage, so that we can reverse bias the collector junction. Now, in this figure, note also how the currents are defined. So IE is going in, IB is going out, IC is going out, and that is consistent to our notation for the PNP symbol. Now, let's start with this reverse bias case as we have just discussed. For this case, we have here the N side, and this is the P side, and it is reverse bias, so majority carriers cannot cross, but minority carriers can cross the junction once they get into the depletion region. And we want this current to be a small amount, and it is actually a small amount only since this one is reverse bias. And in this figure, the transfer of charges is actually represented here. So the reverse current is actually made up of the electrons from the P side to the N side, and of the holes from the N side to the P side. Now, for the other junction, we are actually forward biasing it. So we have here a forward biased junction. Now we have here the P side, and here is the N side, and so majority carriers can cross the junction. Now we designed the BJT such that the emitter is heavily doped, and so we have here a heavy doping for the P side and a lighter doping for the N side, which is the base. And so most of the charge that is crossing the junction would be made of the hole. So this one the holes here is represented by this diagram, and the electrons getting to the P side is represented by this one. Now, for our normal diode case, this injected minority carriers will eventually recombine. However, for the case of BJTs under forward active, we don't actually want them to recombine, and we want them to get to the other portion, which is the collector. So this is why we are actually saying that the emitter emits carriers and the collector collects carriers. Now, unfortunately, since the base is an N-type region, so there are a lot of electrons, and we are trying to pass a lot of holes in that region, then the probability that they will recombine is relatively high. But we want that to minimize that, and to be able to minimize that, we need to actually make this with small, such that the time for which the holes can possibly encounter an electron is relatively slower. So we want most of these carriers to get to the other side. Now, once they recombine at the base, so this hole here will recombine to this electron here, and they will recombine. So that represents some current that is not able to get to the collector. Now, we can actually define the currents here as some IEN and IEP to represent the current due to holes and due to electrons, and here collector current due to holes and collector current due to electrons. Now, note the direction. Since holes are flowing to the right, then IEP is positive. Here, electrons are flowing to the left, and so the current must be positive rightwards. And it is actually consistent with our IE direction, and what we will actually do is to add IEN and IEP to get IE. Now on the collector side, we have ICN. This is again consistent with the flow of electron to the left, and ICP, which is the flow of holes to the right. So this ICP is composed of this one and this one, and we can actually sum these two to get IC. Now whatever is left by KCL, then that would be the base current IB. Now IB is going upwards, and that is consistent to the expectation that electrons are going downwards. And this scenario also explains why the BJT is called a bipolar device, since the carriers that flow through the device is composed of both electrons and holes. Now note that this current here is actually some electron going into the base from the collector, and that can be seen as some electron going out of the base from the device. Now this electron here that is recombining with the holes is actually some electron flow going from outside of the device into the base, and this electron flow here at the left is also going into the device through the base. So this IB here, for the most part, can be decomposed into these three major components. This current here, this flow of electrons here, plus this flow of electrons here, minus this flow of electron here, but we have to flip the direction since this is the flow of electrons. So what makes up a good transistor, or what are its features that makes it a good transistor? So going back in the forward active case, we don't want the injected carriers to recombine into with the electrons at the base region. We want most of these holes right here to get to the collector side. So we do not want them to recombine in the neutral base region, and that basically means that this ICP, we want it to be mostly composed of this IEP. Now we note that since this junction here is reverse biased, then this current component here should ideally be very small, and that ideally this ICP is composed of this this flow of holes right here. And now to be able to achieve that, usually by design, we are making the width of the depletion region to be much less than the diffusion length in the base, since the diffusion length is the average distance that carriers travel into the material before recombining with majority carriers. And since we don't want them to recombine, then the width must be much less than this value. Also, the emitter current must be comprised almost entirely of carriers injected into the base rather than the carriers injected into the emitter. So this emitter current here is actually referring to IE. So we want this IE to be comprised entirely of carriers injected into the base. So that is this flow of carriers here. For the case of PNP, it is IEP, rather than the carriers injected into the emitter, which is this current IEN. And so we can translate this as we want IE to be approximately IEP only, and that would happen if IEP is much greater than IEN. And that will happen if the emitter doping is much greater than the base doping, and that's why we actually have the emitter to be always heavily doped, or the most heavily doped portion within the material. So in a bit more detail, under active bias, there are base current components. So the base current consists of majority carriers. In the case of PNP, majority carriers in the base are electrons that must be supplied, number one, to supply the recombination that is happening in the base of injected minority carriers, meaning the holes injected into the n-type region from the emitter. So this number one right here is this current component here, number one. The base current is also affected by the injection of carriers into the emitter from the base, because the junction EB is forward bias, so some majority carriers from the base can actually be injected into the emitter. So this is component number two. Component number three is the reverse saturation current into the collector. This is actually ICN. So this is component number three, which in the opposite reduces IB instead of increasing it. So this current, this electron flow can actually be imagined to be going out of the base. Now there is a fourth component that is not actually explicitly shown in this figure, which is the recombination in the base emitter depletion region. So we have here the depletion region in the base emitter junction. And if we go back, so we have here a diagram of a forward biased PN junction that represents the emitter and the base. So this injected holes here is this one, and the injected electrons is this one. And since carriers are actually crossing the device, then there are more electrons in this region and more holes in this region than it normally is under equilibrium. Then recombination would dominate. However, it is actually harder for these electrons here, the crossing electrons and the crossing holes, to recombine, since the energy difference is larger. And what actually recombines are the lower energy holes and lower energy electrons. So aside from the usual carriers that are able to cross, there is an additional current that is due to recombination at the base emitter depletion region, which is at the same direction as this current right here. So we can imagine some small flow of hole right here, of electrons right here, to represent that number 4 component. And actually there is some generation current that happens in the reverse biased PN junction or collector base junction, although we will not anymore consider that. These are the common circuit configurations for our BJT. We have the common base, the common emitter, and the common collector configurations, which you would normally encounter when using the BJT as an amplifier or an amplifying device. Now, note that for your amplifier, you have an input side and an output side, and that is obtained with the help of our 3 terminals here. So the common base actually has the base common for both the input and the output side, so that's why it's called the common base. And for the common base, the input is actually the emitter, the output is the collector. For the common emitter, the input is the base and the output is the collector. For the common collector, so the collector is common at both sides, the input is the base and the output is taken at the emitter. Now, this is how you would normally see this circuit configurations or this BJT configurations drawn. So for PNP, normally in our schematic, the emitter is connected nearer to the higher supply voltage. So in all drawings I've shown here, the emitter is on the upper portion, since most of the time we draw the negative or ground at the lower portion. So here the input is the emitter, the output is the collector, and the base is connected to some fixed DC bias or possibly the ground. Now for your common emitter, the input is the base, the output is the collector, and the emitter is connected to some fixed bias, which is usually the supply voltage. Now your common collector is configured as this. The input is at the base and the output is at the collector. Or sorry, rather the input is the base, the output is at the emitter. So for NPN, the circuit configuration would normally look like this one. So we just use the symbol for NPN, and we retain the common portion, so common base, common emitter, common collector, and the input and output are actually also the same. So input is still at the emitter, output at the collector, and the base is always the input. In this portion, the collector is the output. Here, the emitter is the output. This slide shows the different modes of operation of our BJT based on the VEC or VCE and the IC. Since we have a 3-terminal device, we cannot actually fully describe the behavior of the device by using only a single value of VEC, since we also have a third terminal. So instead, we provide different lines or a family of curves to represent different values for the other terminal voltage. Let's focus first on the case for the PNP, since that is what we have just discussed, specifically the forward active region. So here is the illustration of the PNP. Here is its symbol and current notation. Again, for the forward active case, the EB junction is forward bias. So if we look at the table here, for the forward active region, the EB junction, it is forward biased, and specifically for PNP, VEB must be greater than 0, since E is the P side and B is the N side, and we want it to be forward bias, so that must be greater than 0. For the CB case, again under forward active, the collector base junction must be reverse biased, and for the PNP case, VCB must be less than 0, since C is the P side and B is the N side. However, for this plot right here, we are actually given VEC. Now, what happens with this plot? So this is actually what we call the common emitter output characteristic. So if we look back, by common emitter, it means that the emitter is common, the base is the input, and the collector is the output. And with the emitter being common, we can actually look at its, say, bias or voltage as some reference point or at a fixed voltage. Meaning if we draw the PNP symbol in its usual orientation in circuits, so we have this symbol here, and the emitter is at the top, so this is VEC. The minus at the collector, and then the other voltage we are interested at is VEB. Although here, what we are actually indicating in the plot is this IB, and that IB is actually here at the base directed outwards. Now, what does this plot tell us? This specific lines right here is actually for a constant VBE or VEB. So each of those lines represent a constant VEB, and by varying VEB, we are getting varying IB. And specifically for this plot, as we go upwards into the plot, VEB actually increases. And so as VEB increases, the EB junction becomes more forward biased, and there are more holes being injected from the emitter into the base and possibly getting into the collector, and thus therefore we get this higher IC as we increase VEB. Now here is the this plot also shows us the current source like behavior of the BJT under the forward active case, since even as we change the reverse bias at this portion, the current does not actually change that much, because as long as the holes are able to get into the depletion region, then they would just drift into the collector. However, how is this VEC related to the CB junction? Now we'll have to go back to our voltages in the PNP. So we are actually concerned, or we want that VCB is less than 0 for the device to be reverse biased. If we write that into our symbol right here, so VCB is plus at the collector, minus at the base. And if we say perform our KVL right here and solve for VEC, which is the x-axis here, then we would actually get this equation here, that VEC is equal to VEB minus VCB. Now, note that for each of these lines, again, VEB is constant, so this term here is fixed, and meaning as we increase VEC, so if this increases, and this is fixed, and we have this minus sign right here, then it means that as VEC increases, then VCB actually decreases because of this minus sign here. And as VCB decreases, then we are more reverse biased for the CB junction. Okay, and we have noted that even as we increase the reverse bias, the current will not change drastically. So we get this plot for the forward active case. However, there are actually other regions that the BJT can possibly take. We have discussed the forward active. The next easiest to discuss is the cutoff, where both EB junction are reverse biased and CB junction is reverse biased. So if you have two diodes that are reverse biased, then the currents must be very low at either end, and therefore we get this plot right here where the current is actually nearing zero. So IC is approximately 0 and IB is approximately 0, and therefore IE is approximately 0. So almost each current in our device is approximately 0. Now, the other regions are, for example, the reverse active region. It is the case when the role of the collector and the emitter are interchanged. Conceptually, almost the same thing would happen since we still have a PNP device, but since the this time the one that emits the carriers is not heavily doped, then we'd expect a bit less of, or actually much less current being injected into the base, and therefore only a few of them will get into the emitter acting as the new collector. So it's just the reverse. The portion right here is when both junctions are actually forward biased, and that is called the saturation region. So again, as we go here, the CB junction is more reverse biased for a fixed VEB. So let's say this one is for a forward biased VEB but reverse biased VCB. So if we go backwards here, then we're actually activating or forward biasing the CB junction, and so we get to this saturation point. Okay, as a one last note, since at this case we have already shown that at forward active IB is greater than 0, when we go to reverse active, when we just flip the two, then the current at the base will not change direction. Okay, so IB is still greater than 0, but this time for reverse active IC is less than 0, since instead of the holes going out here, we are injecting holes leftwards. So we get this negative current. Now let's look at the electrostatics of a BJT and its energy band diagram. In this example, again, we consider a PNP BJT, and what we can say is that under normal conditions, the BJT can be viewed electrostatically as two independent PN junctions, meaning knowing the doping concentrations on the emitter and the base will allow us to plot this energy band diagram and identify the depletion region width, and also the same can be done for the collector base junction. However, we'll have to be careful since one side is PN, whereas another side is NP. And also we mention here under normal conditions, since there might be a case where the depletion regions actually overlap or would have to overlap, and that would cause a change or require a change in the analysis. So far we'll just consider the usual case for PN junctions and apply them to BJTs. Here we show the plots of the charge density, electric field, and electrostatic potential or voltage within our PNP device, for example, in thermal equilibrium. In this case, we can start with the charge density at the emitter side. Again, the emitter is p-type for PNP, and therefore the charge density must be some negative value. and positive for the N-type base, and negative again for the P-type collector. One thing we can actually note here is that the depletion region at the P side is very, very small because the P side is heavily doped. Now the area of this one should be equal to this one, the area of this one is equal to this one, and another thing you may have noticed is that the height here must be the same, since this height here is actually equal to Q and B, where we are using NB now to represent the doping concentration at the base. And since the doping concentration at the base is assumed to be constant, then the charge density at these two portions must be of equal height. And also that means that we are actually assuming that the metallurgical junctions are at this portion. So in this plot right here, the metallurgical junction occurs here and here, meaning this whole portion here is the N-type base. And we are using WB to represent the physical width of the base. However, when the PN junctions are constructed, then depletion regions exist, and so we have these grayed out portions here, although the grayed out portion on the emitter is very thin, that we are not actually anymore showing it. So from the charge density, we integrate it, so we get an electric field. We integrate a negative charge density, we end up with a negative electric field. Therefore, the electric field is pointing leftwards, or from the N side to the P side. And here the electric field is positive, so the electric field is pointing again from the N side to the P side. The electrostatic potential or voltage is the negative of the integral of this one, so we end up with a positive integral here that is quadratic, and then here the plot goes down. So from the point of view of the end of the emitter and the end of the collector, there is actually some built-in potential. And also we note here W. So WB is the physical width of the base. W is the effective width of the base after subtracting the depletion widths on the base side at the two junctions. So WEB is the total depletion width at the emitter base junction, although most of it falls under the base. The depletion width for the collector base junction is WCB, and some portion of it falls under the base. And with this diagram, we can actually infer that the base is more heavily doped than the collector, since the depletion region width here is shorter. And also in this plot, the height here is larger relative to the height here. Also note that this W here is the actual distance that minority carriers injected from the emitter should have to travel before being swept by the electric field at the depletion region at the CB junction under forward active. Let's now define some performance parameters for our BJT, specifically for the case of PNP. So we have here emitter efficiency, which is represented by the symbol gamma, and is the ratio of IEP over IEP plus IEN. So this denominator IEP plus IEN is actually the whole of IE. So the emitter efficiency for PNP BJTs can actually be rewritten as IEP over IE. So this actually tells us that the emitter efficiency is the ratio between the injected carriers that can possibly reach the collector versus the total current, and we want IEP to be approximately IE. So IEN, we want this IEN to be very small since this current cannot be translated to some carrier getting into the collector. So we want this gamma to reach 1. So gamma na ideal is 1. For the next part, we have the base transport factor, or alpha T. This is the ratio now of ICP over IEP. And so ICP is this current here. We're actually assuming that most of this ICP is this current here and only a minimal of this current right here. IEP is the injected current here, and some of this IEP recombines into the base. However, we want that the recombination is very minimal, that almost all of this IEP gets into the collector and becomes ICP. So in our ideal case, ICP is equal to IEP approximately, and therefore alpha T ideal is 1 as well. So next, the common base DC current gain, alpha DC, is simply gamma alpha T. So if we multiply these two right here, IEP over IE times ICP over IEP, and so IEP will cancel and will be left with ICP over IE. And therefore alpha DC represents the ratio of the carrier current that was able to reach the collector from the overall current from the emitter side, including the minority carrier current, IEN in this case. Now for NPN, we'll just have to change the subscripts. So for NPN, gamma is IEN over IE, alpha T is ICN over IEN, and alpha DC still is gamma alpha T, and we'll just end up with ICN over IE. Now let's take a look at the collector current for a PNP transistor under forward active. So the collector current is actually composed of the holes injected from the emitter that did not recombine in the base, and that is this current right here. And the second component of the collector current is the total reverse saturation current of the collector junction, which is represented by this arrow right here. So since holes are going this way, electrons are going this way, so both of the currents are actually going to the right. And so IC is composed of this current here and this total current here, considering the two. So we can actually rewrite that as some alpha DC IE. Since IE is the total current, alpha DC is the common base DC current gain, represents the amount of ICP that was able to reach the collector from the total current IE, and the total current IC must have this additional component ICB naught, which is the current when IE is equal to 0. So if there is no current here, then we don't have this current, and IC will just be this reverse saturation current. Now we can actually transform this equation into this one. So IC, alpha DC, and IE is IC plus IB. So by KCL, IE is IB plus IC, and this is ICB naught. So we can transfer this term here on the other side. So we'll have on this portion IC times 1 minus alpha DC, divide that term back on the right side, and so we end up with this term IB alpha DC over 1 minus alpha DC plus ICB naught over 1 minus alpha DC. And so this one is a fixed amount regardless of the reverse bias in the CB junction. And here we were able to relate IC and IB, and we define this term here, alpha DC over 1 minus alpha DC, to be equal to this beta DC. Okay, and that is approximately the ratio of IC and IB, assuming that this ICB naught is negligible or very small relative to the other currents in the device. We can actually lump this ICB naught over 1 minus alpha DC as this term ICE naught. So given that we know that the ideal value for gamma is 1 and alpha t is 1, we also know that alpha DC is equal to gamma alpha t, and therefore ideally gamma or alpha DC must be equal to 1, and therefore this beta DC right here is approximately 1 over 1 minus 1, and therefore the ideal case for beta DC is infinity. And what does this tell us? This beta DC will approach infinity not because IC approaches infinity, but rather because IB is very small. So we want this IB to be very small for our BJT to be an efficient amplifier of current. And we are actually using this beta term right here in most of our circuit analysis involving BJTs. So in summary, we have introduced the BJT, the PNP, and the NPN, the terminals, emitter, base, and collector. We have shown the conventions and notations for the currents, and we can actually write KCL equations based on this notation, and also voltage or KVL equations. Note that in the previous slide we mentioned that if we know, say, VEC and VCB, then we can solve for VEB, or if we know VEC and VEB, then we can solve for VCB. That is true. However, say we know VE only and VB, if we only have those two information, then we cannot solve for VC. Okay, what we need to have is two voltages across two terminals. Okay, we cannot solve the third terminal voltage if we only know the two terminal voltages, because if we know V and VB, then we just know VEB, and we cannot solve the rest based of it. Okay, and then for electrostatics, in drawing the energy band diagram, we can actually use our normal analysis or usual analysis for PN junctions, and we'll just have to take the two junctions or analyze the two junctions independently. Again, that is under normal conditions. Among the three, the emitter is the most heavily doped, ideally, and its job is to inject majority carriers into the base. Now, the base is a lightly doped portion of the device and ideally very thin relative to the minority carrier diffusion length to minimize the amount of recombination that happens within the base. And with that, it allows most of the emitter injected carriers to reach the collector. The collector is a lightly doped region and it collects or gathers the carriers from the base. Now, how the um, doping concentration of this collector must be relative to the doping concentration of the base will be discussed in a future lecture. We'll see what are the advantages of making the collector heavily doped or the advantages of making it lightly doped relative to the base. So lastly, we have introduced the performance parameters, the emitter efficiency gamma, the base transport factor alpha T, the common base DC current gain alpha DC, and the common emitter DC current gain beta DC. And that's it for this lecture. Thank you very much.